So I guess I have to get used to the system setup. It's slightly different from last time. And hello, try to make yourself comfortable if you want to. And also, I think some of you already submitted your first homework, and I think that's pretty much some exercise on advanced calculus, I guess. And the new homework assignment will really have some engineering optimization on top of that. And thank you. And I also realized that some students use type-in answers, and it's very nice LaTeX setup for the homework, and that's something I would encourage. And I think last semester I taught information theory and learning course. I think Mr. Wu provided some LaTeX template just for submitting homework if some of you want to type in and learn a little bit using LaTeX. So I'm not sure if he's willing to maybe provide the same source so that I can post on Blackboard. Do you mind if you just email me maybe the homework template so that I can just try to share the source to other students if they're willing to learn. And also Mr. Yu Liu also did something very similar using LaTeX for the typesetting. And also looks very concise, only single page, right? Okay. And I saw some homework submissions like maybe 4 to 5 pages. Of course, it's not really the quantity that matters. Okay, but for computer assignment, I do hope that when you submit the work, you'd better use proper typesetting so that it would look nicer when you print out your report. And also, I would encourage electronic submission if you attach the MATLAB code and also describe about the environment and also how to run your code to generate results, figures, results, or plots. That would be much easier for me to grade the computer assignment. Okay, so let's get started. And before we get into tonight's lecture, any questions about what we did last time and also the homework, and any problem accessing course Blackboard, or maybe any questions regarding using the Blackboard? Because I hope it's not just me feeling that the upgrade of the course Blackboard gave me a lot of trouble. I cannot find some specific function, and sometimes when I try to update some material, the updating process takes unusually long time. I'm not sure when you download some file, you'll encounter any difficulty for that. No? Okay, so probably it's just me. Then that's good. So it's because that's just one-time deal. If I upload some electronic file, then I think everyone can actually use that. Okay, so tonight, I think we will talk about optimization problem, and we will mainly focus on just one-dimensional optimization problem. But before we get into that, I think we need to go over some mathematical description about the problem. I also try to recap what we did last time, and some definitions and some discussions about certain optimization techniques that we made it a little bit formal last time. So basically, engineering optimization problem is about finding what maybe maximum or minimum of some what we call the objective function subject to certain constraints. in general, the variables that we are trying to optimize are sometimes called decision variables. And it takes values either in continuous domain, like in real numbers, or in discrete domain, like maybe integers, or maybe some categorical values, which we will not talk about that now. Maybe only in the very late stage of this course, we are going to talk about so-called combinatorial optimization problem that has decision variables like that. So when we look at the objective function and the constraint, we can basically characterize the optimization problem into different categories. For instance, we can say optimization problem is unconstrained optimization, which means, I'm sorry? There's no constraint on the decision variable. Is that very accurate? I would say sometimes there might be constraint, but the constraint is usually just like the boundary condition. Like maybe it has upper lower limit, but we don't have complete constraint. Like for instance, you have decision variable x1, x2. You say maybe x1 plus x2 cannot be greater than 1, or so on and so forth. There's no such kind of constraint. So that's what we call unconstrained optimization. On the other hand, we can have so-called constrained optimization problem, which means we have constraints in terms of a function of those decision variables. And sometimes the constraints can be linear or nonlinear. The constraints can be inequality constraint or equality constraint. Okay? And also, we can classify optimization problem into so-called linear program or nonlinear program. If an optimization problem is called a linear program, that means what?
Both objective function as well as the constraints, all are linear functions of the decision.
Okay, very good. So both the objective function and the constraints are linear functions. And if any of these is nonlinear, then we simply say it's a nonlinear program, okay? And why we want to characterize the optimization problem like this?
To find the maximum or minimum of the function in that.
Well, I guess it has something to do with how difficult to solve certain type of problem. For instance, a linear program is relatively easy to handle by computer. And nonlinear program is considered more or less difficult. And tonight we are going to maybe give you some idea about the difference of these two types of problem. And also try to gain some insights on usually how you can use computer algorithm to solve different type of optimization problem. And also, I think some of you already started looking into the first computer assignment, which actually use MATLAB or maybe some other software to visualize the objective function in terms of the contour plot, and also visualize the constraints so that we can basically see so-called feasible region, which means what? And some people call feasible set, which means what? If the decision variable takes any value in this set, it will satisfy all the constraints. If it's unconstrained optimization, you don't need to worry too much about that, the feasible set, because whatever the region that you can take the value, usually you can just use that. But for constrained optimization, sometimes by identifying the feasible region, you can actually see some properties. For instance, if those constraints are linear, then the feasible set looks like what? It actually has a name called Yeah, polyhedron, which means what?
Intersection of where the lines intersect.
Well, it is a special case of a convex set. Anyone knows what convex means?
Yeah. A set is all convex if you take any 2 points in the set and you
Okay.
join those 2 points by a line, that line is contained in the set.
In the set, very good. And later we are going to also define convex function based on that. Based on this kind of property, you draw a line and try to say, well, the function value is within this interval should be below the value on this line. Okay. Or maybe in some cases, like in this case for linear objective function and linear constraints, of course, it is still considered convex programming. It's a special case of convex programming. Even if we have a so-called nonlinear programming problem, still if we can make it like a convex programming, usually the solution will be relatively easier to compute than a non-convex program. And we will see that shortly. So for linear programming, we see that it has a linear objective function, and also it contains linear constraints. And also we see the feasible region is like a convex set, which actually is considered what? A lot of line segments for intersect so that you have some kind of polygon type of shape to describe about the feasible region. And also another interesting aspect is that if you want to get the optimal solution, is it inside this polygon, or is it on the boundary? Or for a linear program, if you want to find the optimal solution, can it be inside? Can it be at the boundary? Usually, it will be on some vertex of this polygon shape. Why? Well, if you think about the constraints actually draw like a line that specify what so-called, some people call that isocast or profit curve. These straight lines or planes are like this. Any point on that line means what? Something like if I exchange variable, let's say x1, x2, the profit, or you can say the equality part will not change. So that's like the boundary of your inequality constraint. And we always try to make some trade-off based on that. So you can see when you have all the constraints being satisfied, if you want to maximize the revenue, then usually you will end up with extreme point at the optimal solution, if an optimal solution exists. So this is a little bit abstract, I guess, but here's some intuitive example you can see for finding the optimal solution of a linear program. Okay, so the objective function is to maximize some revenue. In this case, it's a combination between variable x1 and x2, and we want to maximize this subject to these constraints. And both variables x1 and x2 are non-negative, and also x1 should be less than or equal to 6, which is this line. Okay, and then about this constraint, 20x1 plus 10x2 is less than or equal to 160. We have what? A line like this. Okay, that's another line. Okay, and then another constraint is 10x1 plus 15x2 is less than or equal to 150, which gives you another straight line like this. okay? And because both x1, x2 are non-negative, so we only look at the first quadrant of this, starting from 0, and then we can extend this. And these three constraints put the feasible region to be what? Somewhere below, right? It's something, it's the area below this line. So overall, what's the feasible region? It should be where? This thing, right? From here to here, to here, to here, to here, this area. So this area is called feasible region. And also the shape of this looks like what? A convex set, which we gave it a name called that polyhedron, okay? And that's basically what a linear constraint optimization problem looks like, in some graphical visualization. And what if I have 3 variables? Then the constraint will not be something like this. It will be in 3-dimensional space. How do I visualize that? Well, you can think about like a 2-dimensional plane intersect with each other so that you have some kind of
line. Intersection will be a line instead of
yeah.
a point.
Well, the shape may not be something like this, but you can say if you take a 2-dimensional slice, it will look like somehow like this, but it will be in a 3-dimensional space. And that's also called a polyhedron. And of course, sometimes you have to use your imagination if you think about 100 decision variables in linear programming. Then we cannot directly visualize something like this. But what we do know is that usually the best solution will be where?
Based on linear constraints?
Yeah. The optimal solution will be on some extreme point. In this case, will be somehow like this point, or this point, or this point, or maybe this point, right? These are like extreme points. And sometimes, if you can see, this is some kind of line segment about the objective function, and that's the total cost, which is 20,000 when you take x1 equals to 5 and x1 equals to 4 and x2 equals to 5. Okay, and this line you can push, right? You can push along this direction in order to increase the value, right? And of course, the slope will not change. That means this looks like some kind of, in 2-dimensional case, it's a line. In 3-dimensional case, you can think about like a plane. Okay, so you push this to some extreme, but where do you think that you can get the maximum value? We just said that the feasible region is this shape, right? So this straight line should be what? Tangent to somewhere, something like you can push this to the extremal point. It's either here or here. I think in this case should be here, right? So you push that into the extreme case. Here you get value, I think, 40,000. That's this extreme point. And of course, you can push to here, but you can still push further, right? You can push to here. And now you cannot further move away. So this is the extreme point. And that's where you get the solution for linear program. Any questions?
So my thinking is for linear, it always a plan. a straight plane, no curving, no curve?
Well, because you have linear constraints, and linear constraint usually can be written as some kind of a hyperplane in high-dimensional space. In this example, because we have two variables, so you can see the constraints are like straight lines. Okay? But in fact, if you have three variables, you will define this constraint like what? Well, maybe I should switch to document and see if I can draw somehow here. Let's say if I write variables x1, x2, and then if I have a constraint, I can say x1, x2 multiply what, 20 and 10 is less than or equal to 160, right? And of course, if you want, you can say in general, it's some vector C transpose, and then some vector I call x is less than or equal to some value, which I just say A. And in fact, this could also be written in a more compact form, like less than or equal to 0, because I can always introduce another additional variable to take care of the constant A. Okay, so if you look at this, if you say, if this equality is active, which I can write just say vector C transpose x equals to 0. And that's some linear equation for vector x, and which is what? Well, which is geometrically, it's like what? A hyperplane, okay? So that means whenever you have an inequality constraint, that means it's part of the hyperplane. It's either up or down. And then you have everything, all these hyperplane intersect, which will form what we call a polyhedron. Okay? And then basically, by intersect among all these things, you can have many extreme points. We know that the optimal solution will be on one of these extreme points. So what can we do? If we want to find the optimal, what can we do? Well, intuitively, like what Mr. Liu just said, we can check every extreme point and see which one gave you the maximum, right? And in this case, we can check this, this, and this. But graphically, we can see when we push, that's to the extreme, right? And also, depending on the slope of this objective function, the extreme point will change depending on the slope of on the slope of these two constraints, right? So geometrically, you can see that. But is this the best way to find the optimal? Why not?
Because then you need to check. Because, for example, in this case, you just checked with one of the extreme points.
Okay.
Why didn't you check with the other one?
Well, we should check all these four in this case. And then we say this one should be the optimal solution.
So, for example, in this case, we can check it because we have
Yes.
3 or 4 points.
Yeah.
But for example, if there are many points.
Yeah. I think that's a very good point, because when you get into some real engineering problem in industry, the linear program is usually of what kind of size? Maybe 10,000 decision variables for you to optimize. And then how many extreme points do you think? If I have, let's say, 100 constraints. You think it's like a 10,000 multiplied 100? On what scale, intuitively?
5050.
Not a very educated guess. So,
We have 10,000 variables
and 100 constraints. Like what kind of order?
Okay, so the constraints apply to each variable.
A constraint you can think about like just a hyperplane involving with like all these variables in that high dimensional space, and then they can intersect to create extreme points.
Any two of them can intersect. Any two of the lines can intersect.
Yeah, and also that's
100 choose two?
well, it's not very easy to visualize, but maybe let me ask you guys some other interesting questions that may help you to think a little bit further. For instance, let's assume that you have a watermelon. And then, for instance, let's say you can cut it, like using a hyperplane, you can cut it like by half, right? That means you can separate, basically a constraint means it's either on this side or on that side. So you can basically say, well, originally you have a watermelon and then you put that into half, right? That means based on constraint, because of the sign of the constraint, you can put that into two possible feasible regions. Yes?
If it's two feasible regions, you're cutting it in the y coordinate. You can still cut it in the x coordinate.
Yeah.
So that makes it 4 functions.
Okay, so basically, let's say if you have two constraints, basically if you can think about you can cut this watermelon twice, then how many pieces do you get? 4, okay? And if you can cut it 3 times, how many pieces can you get? Like a maximum 8, okay? If you cut it 4 times, how many pieces can you get? 16? Is that feasible? Okay, in this case, because you only have 3 dimensions, so what?
So the force cut cannot, make every part.
Cannot touch all these 8 regions.
Yes.
It can touch how many in the maximum?
4.
Only 4?
7 of them. Anyway, 4 cards get 15 pieces.
Get 15 pieces. Okay, so in fact, if you can visualize, you can actually, yes, like what Mr. Gang Liu just said, you can actually touch 7 pieces. And that's the maximum. Of course, later it will be much more complicated. But think about each card will create somehow like some extreme point, right? And then think about those regions, different regions will have to be exhaustively evaluated because of the choice of the sign on your inequality constraint. So what I'm saying is the extreme point in the high dimensional space usually grows, not like just multiply the decision variables, but what? It grows more or less exponentially fast, which is a huge number if you think about you have, let's say, 10,000 decision variables, you have 100 constraints. I would say most existing computing device, including some supercomputer, cannot handle exhaustively search all the extreme points and try to find the optimal solution. Okay? So that's interesting. Think about, originally we are dealing with what? Continuous type of decision variable. We are searching more or less a region. Now, if we look at the property of this linear program, in fact, it boils down to searching extreme points, which looks like what? Some kind of combinatorial problem. Unfortunately, this combinatorial problem is very difficult to solve if you just search those extreme points one by one. So what can we do? Well, in this case, we want to find the global optimal y because we know it has to be in one of these extreme points. But the problem is how. We don't want to exhaustively search that. And I'm not going to talk about the details tonight because the technical challenge to describe about the two different searching philosophies in solving linear program deserve maybe detailed exposition in the subsequent lectures. But I want to give you some idea about, for instance, in general, when you have such kind of problem, what engineering intuition you want to gain from designing efficient algorithm. One argument is that I don't want to search every extreme point because what? Somehow because of the geometry. Think about, for instance, if I know this is the slope, then if this is the shape, for instance, anything below, is it possible? I would say the extreme point in this case, think about the slope. It has to be somehow from here, the slope is below to the slope which is greater than this, right? The transition part will describe about this extreme point. Can you guys see this? Because if you think about, this is the slope below this, and that's the slope greater than that, and then this extreme point is good. What about this extreme point? It is no good. Why? They are all above this, so it's not really a transition. And that's important geometry. And you can actually use this intuition to apply this kind of smart search in high-dimensional space, which eventually will give you so-called simplex method. I think if some of you heard about the history of linear program, then you probably should know that this actually was invented, I think maybe in the era probably after World War II, right? And George Danzig, who worked for the US, I think on a project for US Air Force, actually thought about many decision problems which can be written in terms of linear objective function with linear constraints, can be systematically treated by using so-called smart search method. And he gave it a name called that simplex. And then later, this method has been refined and polished with a lot of good algorithm that can be implemented using computer. And nowadays, this becomes some routine. You can easily find linear programming solvers even using Excel or MATLAB, or maybe professionally, you can have commercial linear programming solver that can solve large-scale problems. And another idea, not by just searching the extreme point, like I think some students already maybe thought about, is to not only search those extreme points, but what? You can say you can still go from the inside and try to approach to the optimal extreme point in a smart way. Later, we are going to say, well, how can you go like something? How can you really go to a direction like that? You can say, well, I can always treat the constraint as some penalty to the objective function and put some weight. If you violate this constraint, I will penalize you by saying that no, this, even though you maximize the original objective function, but because you are violating the constraint, I will penalize you, depending on how significant you violate. And then, of course, if you are not violating this, I want to see how to approach to another good solution inside. And I keep moving toward where? Some boundary, right? Hopefully, if I can control my direction eventually toward the optimal extreme point, then I get a good solution. And that's a totally different philosophy. And also, it can be shown, also this also works, which boils down to a very important type of optimization algorithm, which is called interior point method. Later, we are going to talk about that. So for now, just want to let you know that linear programming usually is relatively easy to handle by computer software because it has nice properties so that we can find efficient algorithm to get to the extreme point fairly easily. Well, it's not really fairly easy. Later, we have to talk about computational complexity and also some problem we call that it's in polynomial type, p-type, or some problem is non-polynomial. Sometimes we call NP. And I think last time I mentioned that in computer science, there's a one direction called theory of computation, which studies like what type of problem is characterized by P or NP. And also there's a very important or outstanding mathematical question to be answered, which is whether you can find some procedure to solve non-polynomial type of problem, which we call that NP hard problem in polynomial time. And something like whether P is equivalent to NP, well, in some rigorous theoretical setting. And that's important mathematical question, which we don't have answer, but most people would believe that it's not true, meaning that we don't have any hope to solve like exhaustive search type of problem using modern computer efficiently. So let's look at some property for linear program. We see that the feasible region is a convex set, a polyhedron, and also the optimal solution is on one of these extreme points, which is pretty nice. We can say, well, we can find, some people call the global optimal solution, because there's no such thing called local. Later, we are going to talk about what do we mean by a local optimal, which means in my neighborhood, I locate my neighborhood, I'm the best, but I cannot go all the way to the whole feasible region to say, yes, I am the best among all the feasible solutions. Okay, so if you look at the differences between linear program and nonlinear program, we can see that usually we don't have such a nice property about the linear program. The feasible region may not be convex, and what? The optimal solution may not be on the boundary, and may not exist at all, okay, and that's important. And sometimes can be inside, can be at the boundary, may not be at some extreme point. If you are not fully convinced, let's look at another example. Let's say a company can produce some good using capital and labor. Let's assume that K units of capital and L units of labor yields the product K multiplied L units of good, okay? So capital can be purchased at $200 per unit, and labor can be purchased $1 per unit. Let's assume that we have a total budget of $40. So how can we basically produce the maximum unit of good? Is this problem clear? Okay, so if you think about what's the objective function in this case, Okay, so you maximize the product between K and L. And what's the constraint? The total budget is no greater than $40. And we have to purchase what? Labor and, well, let's go back. We have to purchase certain unit of capital and certain units of capital and certain units of labor, right? And in this case, that's the cost of purchasing labor and capital. Okay, so how do we solve this problem? Well, yes, it's a nonlinear program because the objective function is a nonlinear function of the two decision variables, right? So what do we do? Well, I think if you already looked into the first computer assignment, you probably have not, okay? So you should know there's one appealing approach to handle like two decision variables, which is what? Just to visualize this, right? Try to see how the constraint affect your feasible solution and try to do a contour plot of the objective function, okay? So in this case, you can say, well, if we ignore the budget constraint, then we can draw some isoprofit line for the objective function, and you can rewrite this, which is inverse proportional to the budget, the capital is inverse proportional to the budget, and then you can plot this function for different value of z. So that gave you like how you have these different lines. And you can see these are something like a k multiply L equals to 1, 2, 3, 4, and so on, okay? And these are like somehow like contour plot of the objective function. And what? We need to see the constraint, right? So the constraint is what? Somehow like this, right? That's the constraint, which says that the total budget should be what? $40, should not exceed $40, which means what? This is the line, 40 minus 200K, okay? And then we are looking at what? Somewhere under this line, right? So what's the optimal solution to this? You move this contour until you find this contour to be what? Tangent to this, where if this curve touches this straight line, at that point you get what? The maximum for the product of this K and L. K and L, right? So what can we say about this? Well, in this case,
how do you know that in this case the extrusion will lie on the line?
How do I know?
Yeah,
that's a very good question.
It's not a linear problem.
Yeah. So it's not always the case you can find a tangent point here, right? And sometimes it may not be, it doesn't exist. And sometimes the point may not be unique. And I think these are various issues we have to consider. That means for nonlinear program, the solution actually can be very different from what we see from what we see in linear program. Okay. Fortunately, in this case, we can still get to some optimal solution by just visualizing this. But what we can say is that a nonlinear program usually has something very different from the linear program, where the optimal solution is not necessarily an extreme point in the feasible region. And sometimes it might be, even if the feasible region is a polyhedron, still the optimal solution may not be there. But in this example, we can see that still optimal solution is on the boundary of the feasible region. I think one question is whether this is always true in general. No, why not?
Because your objective function may be nonlinear. So
yeah, so you can create very simple example. For instance, even a quadratic function where you have an interval that covers the actual minimum in this quadratic function. So if you think about a simplified version of a location problem with using Euclidean distance, try to basically find a location that you can say can minimize the total distance to different. You want to build, for instance, you want to build a plant that you can say, well, try to minimize the total distance to different customized warehouses. And in general, when you try to do that, for instance, in this case, let's say I just want to find one customer located at a 2, 2, and then I want to say, well, how do I minimize the Euclidean distance for some location x and y? I want to minimize this. But let's assume that you cannot directly put x equals to 2 and y equals to 2 because the facility location has some constraint in a particular area. And then what will happen? For instance, let's say suppose you can only move your facility in the region like a square area between 0 and 1. In this case, we have the constraint that both x and y have to be within 0 and 1. Okay? So is this a linear program? No, even though we have linear constraint. We can see that the full problem is like minimize this nonlinear function subject to this kind of constraint. Okay, so where's your optimal solution?
1, 1.
It's at 1, 1. Why? Well, one easy graphical approach is to say that, well, this is the equal Euclidean distance to this point, right? That's like some contour plot. And then what? We just do this, increase until somehow it touches your feasible region. And that's where it touches, okay? So in this particular case, we see it is at some extreme point of your feasible region. Unfortunately, this may not be the case for some arbitrary boundary conditions. So is this true in general? I would say no. So if, to simply put, if we allow the feasible region to be from 0 to 3, what will happen? Of course, you just select x equals to 2 and y equals to 2, which really give you the minimum, right? And that's 0. And the minimum value for the objective function is 0. You cannot go below that, right? So which means, in fact, you can shrink down to here, okay? And if you expand, then the value of your objective function will decrease because that's the Euclidean distance to this point. Of course, the extreme case is just to put your warehouse exactly at your customer. So in this case, you can say the optimal solution is indeed in the interior of your feasible region. So intuitively, I hope that everyone agrees. For general nonlinear program, we don't have some nice structure of the optimal solution that we've seen from linear program. And also, we need to have essentially different approaches or concepts to help us solve such a problem. Okay, so let's take a short break. And after that, I think we are going to at least intuitively talk about how we try to solve some kind of a nonlinear optimization problem. And of course, we will start with something very simple. Okay, you finished?
I tried to use the chain.
Okay, thanks.
459 G required.
I'm sorry?
459 G required. I mean, I just put the thing down there.
Well,
Required to.
Yeah, of course, it would be nice if you can simplify a little bit, because if you have the.
I wanted to, but
Okay, yeah, of course, I will take a look.
Question.
Sure.
What is the rules on using calculators of sophistication? What levels?
Like a TI-92.
Well, if you are familiar with the TI calculator, of course you can use that.
Real math, I use that for my homework.
Okay, sure, no problem at all.
I got like 11 pages.
On the symbolic calculations?
No, I did it longhand.
Okay. Well, what I'm saying is if you are familiar with some symbolic toolbox in MATLAB, you can also use that.
That's the next thing I was going to ask you. I brought my laptop.
Okay.
You can have a little time after class because it's been so long since he's probably older sooner than I am, but we both kind of rust. And I've just played with some of the examples on MATLAB. Okay. And maybe kind of point us in the right direction.
Sure, yeah. And also, if you want to stop by some other time, I mean, in my engineering building office.
We've been real busy this week.
Okay.
But yeah, that'd be great.
Well, maybe we can maybe arrange some discussion, just purely focus on MATLAB programming. I can also provide you some resources for you to practice if you want.
Oh, really? Yeah, that's good.
Yeah. Okay.
Yeah, if you get some examples where we can just, particular things that are more along the lines of what we're trying to do. Yeah.
Okay.
I just want to make sure because I did use the calculator a lot.
Okay, yeah, of course, if you're familiar with the TI-89 calculator, then just use that for whatever.
That's way after his time. This guy's old.
Oh, I don't know. Close. I don't know. You got to see what I said.
Are they actually just wrong or right, or it's partial credit?
Well, I can get of course I get partial credit, but I think the most important thing is that after you get back your homework, you still try to work on the problem that maybe if you made a mistake, try to understand better.
Okay.
Okay. So you already started your computer assignment?
I looked at it. I haven't done it yet, but I think it's doable.
I think I did it, but
okay. Well, if you want, you can submit later. But of course, if you already finished, that's fine. You want to submit now? That's fine. Okay, sure. Okay. Yeah. Yeah. I think that the answer is correct.
Yeah, so it's this problem with the painting. Right?
Oh, yeah.
Yeah. And it's a problem.
16, 17.
Yeah.
Because this is the second edition. So
Oh, so you have the copy from the second edition, and the problem number may be different.
problem number? Yeah. So I need to check it. Right?
Okay.
This is on page 90 something, I think.
Oh, the next homework assignment, you already started looking into that. Okay, good.
It was not hard.
So
They gave me the trig identity for the second one, so it's easy.
Yeah.
So it's a 16 and
I
a
think it's
7.
16 and 17.
Oh, you already finished?
Yeah, I was.
Okay, take a look.
I was feeling good.
So 16 is supposed to be like some square.
I guess some explanation is needed to say this is really the optimal solution.
Okay. Well, I took a derivative and I set it equal to 0.
Well, that may not always give you the optimal solution, so you.
Do you want me to check second derivative? Or?
Well, at least that's
Okay.
the necessary condition. I mean,
Yes.
to get a stationary point. But in this case, actually, you can verify it is.
The second derivative.
Yeah.
Okay.
And also even check second derivative, still it's only like a local maximum or minimum. And in this problem, in fact, you can say that's really the optimal solution.
So I think there's only one.
Well, because this is actually like a quadratic function,
Yes.
which is
Has only one.
is a convex
Right.
function, so that's important
Right.
to identify. So you can really say, yes, that's the best solution you can come up with.
Something like this. And then you have to show them the graph. The different probably plots out. See the contours.
They give you the units too? Yeah, they do. Okay. So you have it.
See? Contours and the functions. To the line.
Yeah. I thought it was all self-contained. There's a file and it's like how they go this problem.
Wow, so you go one step further, try to finish. If I assign all the homework assignments for this semester, you probably want to finish all of this.
He's a PhD. That stuff.
Okay.
The rest is a chance.
All right, so I guess let's continue. And I think we already see that nonlinear program in general is much more difficult than linear program. And maybe we should start from something relatively easy, right? We look into what? Of course, for linear program, like what I said, later we are going to talk about how to really handle linear program most thoroughly. Let's first use nonlinear program to at least set the tone on some important concept of optimal solution, or maybe near optimal solution, or sometimes people call suboptimal solution. And I think in some of my colleagues' opinion, it's actually equivalent to non-optimal solution, which is something like, yeah, I know I probably don't have the best solution, but that's the best thing I can come up with. Okay, and we are going to later see the mathematical reasoning behind it and how we may want to improve upon the solution quality. So, of course, we start from the easiest case, like one decision variable and what? No constraint, right? That's the easiest thing we can talk about. Even in this case, still, we can see that it's not really a clear cut what we can do to really find the optimal solution very conveniently. So what we want to do is to just look at some specific single decision variable, one-dimensional optimization problem. Of course, it's nonlinear program, so the objective function will be what? Nonlinear, which means it can increase and decrease, act strangely. But we first try to say, well, we hope the objective function is continuous, so that we can actually see there's no breaking point at different points. That's easier to handle. And later we are going to require even more. We say that not only the function is continuous, but also differentiable, meaning that what? Well, the derivative exists, but intuitively, what's the difference? For instance, can I have a continuous function which is nowhere differentiable? If it's like what? Can you give such an example?
Nowhere differentiable or not.
Well, can I have a continuous function and a nowhere differentiable? I think this is not really a calculus class, but it's interesting to ask. Maybe Libby has good math background. I will ask her. Well, a square wave is not really continuous when you have this. Yeah. Well.
Periodic, but they're not continuous because they have.
We have continuous functions which are not differentiable at some point.
Okay. How to create a continuous function that's not differentiable? For instance, you can see something like this, right? You can say, I have this, okay? And what? And at that point, you have this triangle type of thing. The left limit and right limit are different, so it's not differentiable. But that's only for one point. And if I want to have a continuous function for every point, I don't want it to be differentiable. What should I do?
At every point?
Yeah.
Not differentiable?
Yeah. Is it possible? No?
Kind of define definition of continuous and differentiable.
You think it's not possible? You think it is possible?
It should be discrete function. I think it should be.
Well, I'm still looking at a possibly a continuous function. But this continuous function should not be something like in the usual way that you can easily see any point in the neighborhood you can find that. So it's something I have to creatively construct somehow to make the limit different from one part to the other. Well, even though it's a little bit against our everyday intuition, but still, it is possible to construct such a function. If you get into any functional or real analysis, probably these are all things you have to exercise that may blow up your mind somehow. And anyway, so that's not really what we care about, but we do know that if you talk about any real function, try to find the maximum and minimum, by looking at the derivative, it's asking for something that's mathematically not very convenient to obtain. But in practice, of course, for engineering problem, we can always assume that we have that. So we restrict ourselves to linear problem. In one-dimensional case, it's actually trivial. Why? Okay, so if without any constraint, you can either monotonously increasing or decreasing or flat. So there's no real meat in the optimization. But even for one-dimensional nonlinear program, we can see a lot of challenges in this case. Well, depending on how we construct that function. Okay, so here's one example where we just look at the value from 0 to 360, where we want to minimize this function f of x, which is this curve, and we want to minimize. So here, this is the actual minimal. Okay, we want to get, but what? This guy is fairly close to that, right? Is it easy to find this point as the minimal?
Well, first of all, that function, you probably have to have a Fourier series or something like that to describe the function.
Well, this function, well, sometimes you may have an analytical form to write, but most of the case, even I gave you the analytical form, you still need to plot using computer tool, using a computer program anyway, right? So here I just ignore the background, saying that that's the function I want to minimize. Okay, and then how do I know this is the minimal solution? Basically, intuitively, well, if I can visualize, then done, right? Otherwise, what? Otherwise, well, this is not convex or concave. In this case, even in some neighborhood, you cannot really see clearly whether it's convex or concave. Well, you can see that, for instance, I think most of you know that if this is some continuous function which is differentiable, there's one important necessary condition saying that derivative should be 0, right? At any maximum or minimal, you have the derivative equals to 0. And sometimes even a stationary point, you can have derivative equals to 0. For instance, y equals to x to the power of 3. You take derivative and set it to 0, you get x equals to 0, which is not really maximal or minimal. Okay, so if you look at this, in fact, you can see you have some maximum or minimum point. And now we can talk about some local optima, or maybe you can say local maxima or local minima. And for any nonlinear optimization problem, if you think about any feasible vector, not just scalar, you can say for vector, that's basically the same thing. If you say, well, I have some point which is greater than all other points in my neighborhood, then that's like what? A local maximum solution. On the other hand, if I have a point f of x where that's no greater than any points in the neighborhood of x, then that's local minimal. And remember this less than or equal to, there got to be some sequence essentially different from this point in the neighborhood. That's actually where the strict equality sign should be true. Otherwise, they are all the same value within that neighborhood. So that's not, so there's no real minimum point. But still, if you want, you can define that as local maximum or minimum. Any questions? So this just sets the tone. I think in most cases, we know this is not really the optimal solution, but because what? Because of the convenience, we can easily, for instance, find the derivative of some objective function. So we set it to 0 and try to use that as a necessary condition to identify if I can find the local maximum or minimum. That means what? I can basically check. It's similar to, like, I know that for linear program, I can always check the extreme points. And here, I can always check derivative equals to 0. And for vector case, what should I check? The gradient direction, which is actually take the partial derivative with respect to each variable and set it to 0. And that's something I want to check. Okay. And here, of course, you may want to ask rigorously, what do we mean by for all feasible solution x prime that are close to x? What does that mean? Yeah. Okay, so which means this is any point that's feasible in that in the neighborhood. That means I can find a sequence of feasible points which eventually converge to this point. Okay, so that's basically says for all this, we can find some epsilon that make this arbitrarily close. Okay, so with that being said, we can see that's the examples of local maximum points. This guy, this guy, this guy, this guy, and this guy. And is that all? No. In fact, there are quite a lot, right? For instance, this guy, right? And this guy, and this guy, right? And this guy. And there are also other local, but this is actually global maximum, and this is global minimum. And other things are all local. Okay? So what can we say about one variable unconstrained optimization? Well, it is important that if you can visualize the objective function, you can always do that, right? It's much easier, but sometimes you cannot really always rely on visualization. Why? For instance, from 0 to 360, how many points do I need to visualize that? 100, 10,000, 10 million? We don't know. But what's the problem? Within here, this is the minimum, right? Within a small interval, of course it's continuous, but still I use discrete points and then I interpolate. Would that be reliable? I really don't know, right? Sometimes if you have a very sharp peak below, very sharp, like some kind of, you can say, I have something like I have a hole which is very deep, but usually you cannot really get into that if you don't sample fast enough. If you don't sample dense enough, you cannot really get to that. So by just visualizing graphically, you get some idea about what the objective function should looks like. But still, it's not mathematically rigorous to claim, yes, this is the global minimum point. Okay? So if we assume that this is a continuous function which is differentiable, then what? At least by checking necessary conditions, by taking derivatives, set that to 0, and find all solutions to that nonlinear function. Then what? Then we can actually examine, right? And how do I examine if this is local or global? Checking second order derivative, right? Meaning what? If in this neighborhood they are all below, then looking at the second order derivative, what should I get? Within this neighborhood, they are all below, the second order derivative should be what? Should be positive, right? On the other hand, if I'm looking into, sorry, should be negative. Negative because you have this kind of shape. And they are all below, and if you have a minimal here, then what? Check the second order derivative, should be positive. Okay, is that all? Yeah, so you still need to evaluate all these points, right? And then try to find which one is the largest, if they are all local, right? And probably that's the best thing we can do.
At least this way you have candidates for...
Yeah, you have some candidates.
You don't have to search the entire function.
You don't have to search the whole interval. Basically, you only search for those candidates to see. If the second order derivative is 0, what will happen? I'm sorry? Well, sometimes you may even need to go for higher order derivative to determine what's going on, right? For instance, x to the power of 6, if you take derivative, get to 0, take derivative, get to 0, and what? Of course, first order derivative is 0, second order derivative set it to 0, x equals to 0 is still 0. You need to keep going until what? Until somewhere you get a non-zero solution, and then you check what? It's positive or negative, and in this case, let's say it's positive, then what will happen? This is y equals to x to the power of 6, okay? Can we find a maximum or minimum? If I set derivative to 0, for instance, in this case, at least I have x equals to 0, supposed to be a minimum, right? And then if I keep doing derivative, what will happen? Eventually, I get some positive number, right? And then how do I know that's a minimum? Depending on what?
Well, it's positive, so shouldn't it be concave up then?
Well,
I think it's like 6th or 7th order derivative.
Well, is it 6 or 7? So that matters, right? So in this case,
The derivative is the odd number derivative or even number.
okay, so if it's odd, that means what?
I forgot which one.
If it's even, which means what? Like second order derivative, that you can determine, right? If it's even, you can. If it's odd, you cannot, because like x to the power of 3, in fact, x equals to 0 is just a stationary point. It's not maximum or minimum. So whenever you have derivative, you take the odd orders of derivative, which you get evaluate at a stationary point, you get non-zero. What will happen? You will say that that's not really a maximum or minimum, right? And otherwise, if it's at the evens order, then you can. in fact. Okay? But of course, this idea is only for one-dimensional case. For higher dimensional case, we have to use gradient direction and so-called Hessian matrix, which later we are going to formalize that. But I think you can essentially find like a vector or matrix representation for vector case more conveniently if you're familiar with this kind of matrix algebra for using calculus for matrix algebra. Okay, so we can say that there are many algorithms that can solve this kind of problem, like just find the local optimal solutions for a one-dimensional nonlinear program. And some of these we will study in this class. And remember, a lot of solvers, like anyone heard about this? Lingo? Okay. And some Excel solvers for one-dimensional case, in fact, they only find what? Some local optimal solution. And if you want to find a global optimum, you cannot just say plug in this solver and I get it, because you need to do some extra work. Why? Because, for instance, even though you have a one-dimensional function, usually you don't have an analytical form. You just gave some function where you plug in y equals to f of x, right? You can evaluate this function, but doesn't say about anything about what? The analytical form of this. And sometimes you can supply derivative at any point of this function. Like derivative df dx, you can have that, but maybe you don't have second order derivative. So those solvers need you to provide information in order to proceed. Okay, and what else? Sometimes it's not so easy to find the maximum or minimum very conveniently, even though for one-dimensional problem. And for instance, if you run this software package, you will see that sometimes for the example that we showed before, they say that local optimal solution is found, and then you have some solution value and reduced cost and other things probably you don't care too much. And what we know is that for a linear programming solver, any local optimal is indeed a global optimal. Because what? Well, because later we are going to see, because actually linear programming is a special case of convex programming. And because of the so-called convex property, we can claim that there's only like a one unique solution. If you have a local maximum or minimum, that's actually global. But can we find some type of problems which also holds that local optimal is indeed global optimal? That's what we are going to talk about. Only for what? Convex or concave function, we can actually say about when a local maximum or local minimum is actually global. If it's convex, looks like this, right? So we can always find the minimum. If it's concave, it's like this. And then you can find the maximum. Okay, so in general, convex program is a very special type of nonlinear program that we can solve the constraint optimization problem efficiently using existing algorithm like interior point, self-dual, interior point methods or some other method that some method that I may briefly mention but not really explain all the mathematical details because of the scope of this class. Probably I can only give you some idea about how the engineer optimization problem should be formulated and how to find efficient tools to solve the problem. Okay, so how can we define convex optimization problem? Of course, we want to know that if we have an optimization which is a convex optimization, what do we mean? Well, the objective function has to be a convex function. And the feasible region has to be a convex set, okay? So you can think about this f of x1 through xn, that's a general objective function defined for a vector of decision variable x in some convex set S, okay? And in this set, yes?
You should put the projector.
Oh, sorry.
Because you got disconnected, so the feed switch.
Oh, thanks. And I should do this. Let me see if that will work. I'm trying to connect to. Okay, I hope this time it works. Okay, thanks for reminding me. And we can see that the convex set is something like if you pick any two arbitrary points in this set, and then you connect these 2 points by a straight line. That line has to be what? Within this set, so that means that's convex. And this circle is convex, okay? And in general, if you think about the intersection among all these hyperplanes, that's convex, right? And for instance, this rectangular shape is also convex. And this is not convex. Why? For instance, you can easily find 2 points here and here. You draw a line, is outside, okay? And this is another case where you put a point here, and point here, because inside it's not feasible, so that's not convex set. Okay, and another interesting question to ask is something like, if a set is not convex, can I use some other set to cover this set, which will become convex? For instance, can I use a convex set to cover that? And in general, how do you do that? Well, by definition, we know convex means what? Any 2 points, you draw a line, it has to be in. And now if it's a non-convex, we know some points will not be in, right? So if we want to cover that by a convex set, the minimum coverage we can construct is like what? You pick any 2 points, you draw a line. If it's not in this set, then I force that into the set. So that's what, like the convex coverage on a non-convex set. For example, here, if I want to draw a convex set to cover this, I should do what? Something like connect a line somewhere here to here, right? Somehow tangential to this, any points below should be within my convex cover. And this is easy. I just fill in this circle, okay? And why this is important? Well, later we will see that even though some problem may not be convex, but what? We try to approximate the problem by using some convex approximation. We know that if we can handle convex program, things will be much easier. So we try to change other problem into that. I think in the first class, I also mentioned that sometimes you have to be creative, right? Like in some cases, you have nonlinear program, and if you introduce more decision variables or adding more linear constraints, you can convert the problem into a linear program, which you know how to solve efficiently. And that's important engineering design or creativity that you have to exercise. Unfortunately, there's no systematic procedure to tell you if a problem can be converted from nonlinear program to linear program. But this we can always do. For instance, if you have a non-convex set, you can always find the minimum convex coverage to that. Okay, so that being said, now we are going to think about, for instance, if a set is convex, then of course any line segment joining any pair of points in that is completely contained in the set. That's the property. Then of course we see that, for instance, linear is important property, like because anything along this line is considered linear combination of the 2 points by different weights, right? So that's important. And later we are going to also introduce some other concept that may be, for instance, any point within this coverage. Later we are going to talk about so-called convex hull. And that's something like you try to make all kinds of linear combination of these convex sets. And also later you're going to see that there are some important properties we are going to use to identify if a problem is convex program or not. If it is not, still some problems can be converted into convex program. We are going to talk about that later. So this is important, and also we can see that if a function is a convex function, that means what? We understand about convex set, which means you have 2 points, you just try to draw a line and check if within any point on this line is within the feasible set or not. And now we are going to talk about the convex function, which is just the shape of the function, like how it increase or decrease, right? And convex means what? Somehow like this, right? And you can easily see it's also checking what? You have arbitrary 2 points, checking the line on this point, connecting this point, and then what? Okay, it's above or below. Okay, very good. So here's f of x equals to x squared. That's the easiest thing we can think about. It's a quadratic function which is convex. So we check what? You pick any 2 arbitrary points, and then you check on this line, any point on this line should be evaluated where that's actually what? No smaller than the function value at this point, right? And in this case, we can see any point is actually above the corresponding value f of x, right? So if you look at this, that's the value lambda x prime plus 1 minus lambda x double prime, and this is x prime, and this is x double prime, and that's the 2 points we chose, and this is actually because lambda is some value within 0 and 1, so we know it's in the middle. And that's the function value is below the linear combination of this value and this value. Is that clear? So that's the definition of convex function. And because of that, we can also talk about so-called strictly convex function. For instance, we see that all these points are strictly above this, right? So in that case, what can we say? this is a strictly convex function. For instance, a straight line, is it convex? By definition, in fact, it is, right? Yeah. Is it concave? You can also say that. So if you say, can you find a function it is both convex and concave? Yeah, it has to be a line. Okay. And can you have a strictly convex and strictly concave function?
No.
Both? No, you cannot, right? Okay, so concave function, of course, is just the opposite. In this case, you draw a line and the value should be what? The function value should be above the value on this line. And here's just another simple demonstration where you have a concave function and f of x equals to minus x squared. And then you pick a point here, and then you pick two arbitrary points, x prime and x double prime. You draw a line. Somewhere in the middle, this point should be below the value f of lambda x prime plus 1 lambda x double prime. Okay. So now we can examine this is a non-convex and non-concave function within what? Within this interval. That we can easily check. For instance, we pick two arbitrary points here, x prime and x double prime. What happened? Well, this line, we can see occasionally it's above and some function value is below. So we cannot. Yeah, so we cannot say it's convex. We cannot say it's concave. It's non-convex, non-concave. And that's difficult, right? Like we say. But if it is convex, then life will be much easier. Even if it's locally convex, still within that region, we can make our life much easier. Here, for instance, if this thing, you just sample the function by different values and draw a plot like this, we never know somewhere in between what will happen. But if you know it's locally convex or concave, then basically life will be much easier because within the feasible region, if the function is a convex function, then we know it has a unique minimum. If it's a concave function, we know that it has a unique maximum. So here, let's say we want to maximize some objective function f of x, where x belongs to some convex set S. Then what can we say? Any local maximum is indeed global maximum because of convexity. But why? I'm sorry? If you think about if I have a concave function being optimized, I can claim that any local maximum is indeed a global maximum.
Because of the uniqueness of local maximum?
Well, that we have to prove, right? So how can we really prove that? Very good. How? Well, I think intuitively you think about maximum means what? Somewhere in the neighborhood, it has to go increase and then decrease, right? And then what? Somewhere you know that any 2 points you draw a line, this line will be below, right? If you have a local that change, then you cannot change again, right? Intuitively, so that means you have only one unique maximum. And that's just intuition, but how do we really prove mathematically? Usually, a very important tool to use is like what Lippi just said, by contradiction. We assume that this is not true. Then we try to reach some contradiction, something that clearly violates our assumption. So this implies that eventually we can say that convex programming or concave programming is easy because there's only one unique maximum or minimum. So let's suppose there exists a solution, what we call x prime, that's a local maximum, but it is not a global maximum, which means what? There should be some other value, f of x greater than f of x prime, right? Now we know that this is concave function. So what? And we already assume x of x prime is what? Local maximum. So what? So of course we can check the property of convex. We look at this is another maybe global maximum, and this is local. So what will happen? We know that for some value, lambda between 0 and 1, we check this, which should be greater than lambda of this plus 1 minus of lambda this, right? This is greater than or equal to, because I didn't say that this is strictly concave, so I just put an equality. But we do know that f of x is actually greater than f of x prime, right? Because we say there exists another global optimal. So in that case, this is actually greater than this. But this is actually just f of x prime, right? Which means what? Somewhere in between, it shouldn't be greater than that, right? So by manipulating this, we reach a contradiction, which means what? There's only one global maximum. And how do we check that? In fact, if you think about when lambda is very close to 1, then what? This value is very close to x prime. And in this case, we know this is greater. So therefore, in fact, this x prime cannot be a local optimal. And that contradicts our assumption that we have a local maximal solution, which is not a global optimal. Okay, so that's indeed a contradiction. So if we look at this example, we can also see that by checking what? Derivative, first order derivative, and what? Second order derivative, we can in fact verify what? If you have a convex function, that means the second order derivative will be what? Non-negative, right? And if you have a strictly convex function, then the second order derivative should be positive, okay? And if you have concave function, then you can check the second order derivative. It has to be always, okay? Yeah, otherwise strictly less than 0. Okay, strictly negative, okay? So this is very important because sometimes you don't know whether a function is convex or concave. You can always check that, right? The second order derivative. Sometimes if you have the analytical form, you can always check if it's non-negative or not. Okay, so maybe let's take a short break and then we try to wrap up the discussion on one-dimensional optimization problem. Yes?
When I was taking calculus, I learned that instead of calling them convex and concave,
okay.
They should be concave up and concave,
concave
down.
Okay, that's another term Actually, I like that.
I don't really know.
You mean convex up, convex down? Or?
I learned this concave up.
Concave up and concave down. Okay.
Yeah, but I don't. Now that I'm seeing the formal definitions of convexity and concavity,
okay.
I don't really know where that came from. But back in calculus, they told me that's what I should
okay,
call
that's fine with me. And I think people working in operation research area probably have different way of saying things. But most people like a convex program because that's the keyword you can search on the optimization literature. Especially I have an online text, I think there's one very good online textbook written by Steve Boyd from Stanford University talking about convex optimization, which is very comprehensive engineering treatment on how certain problems, engineering problems, can be formulated as convex program. And also there's a software called the CVX associated with the textbook, which can be installed with MATLAB so that you can actually write convex program routine using that CVX. And I think I may have some project assignment that require you to play with this convex program software. But of course, if you want to do something on your own, that's also another option.
So if you have a closed three-dimensional surface,
okay,
you have convex is still this definition where you take any 2 points on the surface, then all of the points on the line that joins them.
Well, I would say if you consider just like the surface of a sphere, then if you draw a line, then in fact, that's really not a convex set.
No, I mean like the interior space. Not
the interior, yeah. The interior, I think that's still a convex set.
Right.
Yeah.
And so then in that object, the concavity would be a part that is not convex, yeah?
Well, I would say convex set is about like the feasible region of your objective function. And function in itself, you can talk about it goes up like a convex or concave. But the set has to be convex. When you talk about convex program, that's important. If your feasible set is not convex, things will be much more complicated because you have to jump around. For instance, I can say, well, even though I'm looking for the optimal solution, but how to get there is here and there, have all the barriers. No, you cannot go here. No, you cannot go there. Then things will be much more complicated. Even though you say, yes, I have a nice convex function. But the feasible set is different. So we first have to limit the discussion to convex set.
So for a function with a single variable, so we check the convexity, so we check the second order derivative.
Yeah.
So with multiple variables, we check the Hessian matrix or positive Hessian matrix?
Yeah, that's very good. That's a very good question, and I think you already have the answer.
Okay,
so yeah, you can check the corresponding to the second order derivative for the vector case is Hessian matrix. You have to check whether it's positive, semi-definite, or maybe positive definite on whether it's strictly convex or convex.
Is we have the x to the 6th example.
Yeah.
Does that hold also in higher dimensions where instead of just second order, like the Hessian matrix, you take derivatives of derivatives of derivatives, you know?
Oh, I see. That's a little bit complicated. Because for higher dimensional case, so that you not only you have stationary and point, you can also have so-called minimax type of saddle point. And you can also have some other shapes that we cannot really describe very well. So I wouldn't go that far to examine that. But later we are going to talk about, if you want to have some mathematical rigorous, I would say check the Hessian matrix, but check just some submatrices to see if it will satisfy certain property or not. That's relatively easier than you go for higher order. I don't know how to really put. Usually people use Laplace operator on that. Just keep doing. You know how to do Taylor series expansion, so that's probably the way you can go for advanced calculus for that. Yeah. So okay. So I hope that I can have everyone's attention to talk about why this is very important for the subsequent discussions of the optimization problem. So suppose that we have some nonlinear program that we can identify the region is convex, and the objective function is either convex or concave, because either way sometimes you can change maximizing the objective function to maximizing a concave function to minimizing a convex function. So either way, we can discuss about this. And when you can really have such a nice convex program, then you know that any local minimum is indeed a global minimum. And this is really nice because what? Our goal, of course, is just to find a local optimal. And finding local optimal usually rely on what? Take a derivative, set it to 0, and sometimes that's doable. So even that's not doable, later we're going to see. For instance, you can say because a convex function, you can say a concave function is like what? A hill, right? From anywhere, just climb the hill. You know if I reach the top, the summit, if I look around my neighborhood, they're all below, then I know, yes, that's the maximal solution. Is that clear? So you can always try any algorithm to do the hill climbing. So each step, if I'm going up, then that's good. I keep doing that. Eventually, if you can prove that this iteration will stop somewhere and reach to the stationary point, in fact, you're good, right? So that's the nice thing about convex or concave programming. And because of that, of course, we always try our best to identify if a nonlinear program is convex or concave program. And if it is not really a convex program, what do we do? Later we are going to learn, we try to convert the problem to a convex program. And that's important because the underlying idea is something like if I optimize another convex function where the optimal solution I can show is indeed the same as the non-convex objective function, then I will use the convex one. And sometimes that can be done by so-called changing the problem structure. Later, we are going to talk about the Lagrange multiplier for constraint optimization and also changing the primal problem to dual problem.
Is it always possible?
Not always, unfortunately. That's a problem that, of course, it's like when you formulate an engineer optimization problem, you try to formulate in such a way that's computationally tractable. Meaning that if you can formulate it as a linear program, don't formulate it as a nonlinear program. If you can make it a convex program, then don't make it a non-convex, generic nonlinear program. And this is, of course, for decision variables in continuous domain. And later, we're going to talk about decision variables in discrete domain, and also how can we combine decision variables in both continuous and discrete domain.
No, it may not be possible to exactly get the same maximum or minimum for
Yeah, it's not always possible. That's why only for some specific problem we can do that.
But can you at least approximate the solution by changing the non-convex problem to convex?
Well, you can always do that locally. Something like you can interpolate like a quadratic function within some point, starting point, locally. That's always possible. And also that's a very important numerical technique later we're going to talk about. And another important thing I would like to mention is that you can look at some properties about the convex function so that, for instance, that may help you to identify certain convex or concave program. And later we are going to talk about one step further. Even though it's not the exact convex or concave program, we can convert. For instance, we are going to talk about so-called semi-definite program and also geometric program, which are not exactly convex, concave, but we can convert. And of course, a linear function is both convex and concave. And also we know that if you take the sum, or in fact, a linear combination of two convex functions is still convex. If you take the sum of two concave functions, it's still concave. And also, if you think about convex set, if you take the intersection among a bunch of convex sets, still it is convex. And these are important things you need to know. And how can we recognize if a function is convex or not? In one-dimensional case, it's relatively easy to examine because we can always check second-order derivative. And we know that if f of x is convex function on set S, then the second-order derivative should be non-negative for all values x belongs to S. And what happens in the vector case? If x is vector that involves a set of decision variables, and still we say this S is a convex set, then we cannot say second-order derivative. What I should say is what? It's like the Hessian matrix. What is a Hessian matrix?
It contains all the mixed and all mixed derivatives of order 2 up to order 2.
Okay, so maybe let me just write it down. Try to see if I can use that. Okay, so a Hessian matrix is something like if I say I have f of vector x, which I can write this is fx1 through xn. And then how do I take first order derivative?
You just take partial derivative.
Well, I need to say, for instance, the gradient of this, which is what? Something like a partial f, partial x1 up to partial f, partial xn, right? Something like this. Okay? And how do I take second order derivative? Well, it's like you can think about notation-wise, you can say it's something like this. Okay? And of course, it's in fact a Hessian matrix, meaning that what? It's not really you take the outer product of the gradient. In fact, it's second order derivative, but you need to do what? Something like second order derivative for, this is for x1, and then you have what? For, this is like x2 and x1, and keep going until, for instance, xn and x1. And of course, similarly, you can fill in all these terms until this is for xn, right? Of course, you know that most of the cases, the order doesn't really matter, meaning that you can first take partial f partial x1 and then x2, or x2, x1, in fact, doesn't really matter too much. Yes?
So the matrix is symmetric then?
The matrix is symmetric.
Dr. Chen, we can change the order only if the function is twice differentiable. Otherwise, we can.
I'm sorry?
We can change the order of taking the derivative
Oh,
only
partial.
if the function is second time differentiable.
Differentiable, yes, that's important. Of course, we already assume that the function is differentiable. Twice differentiable. Then we can talk about all this, like changing order and things like that. And like Sarah just mentioned that because this is like a real function, so Hessian matrix is actually symmetric, right? And also we try to examine if this function is either positive definite or positive semi-definite to see if that's a convex function, to see if this is really a convex function or not. Okay? And similarly, if you have a concave function, then the second order derivative should be non-positive, or you can say the Hessian matrix has to be non-positive definite or negative definite. Well, the term doesn't really matter, but you need to use this quadratic function as an example to see exactly what convex or concave function look like. Okay, so maybe let's look at one-dimensional optimization problem. This is our first encounter of nonlinear optimization, the easiest case, but not that easy. Of course, we gain some theoretical insights by first assuming this is a continuous function and it's differentiable, so we can always check the necessary condition, take derivative set, or take the gradient set to 0, and then identify all the stationary points, and then check second order derivative or Hessian to see if this is really a maximal or minimal, and also what? Evaluate to see if it's a global or just local maximal. And of course, this is easy, usually easy for one-dimensional case, but not so easy for multi-dimensional case. So what can we do? In general, we need to use numerical algorithms for multi-dimensional nonlinear optimization, which usually requires solution to one-dimensional nonlinear optimization sub-problem. Okay? So in general, of course, we need to first know how to solve one-dimensional nonlinear optimization. And then we say, well, if we know we have this routine, later we're going to talk about how to build more complex optimization algorithm based on that. So this is very important. For unconstrained one-dimensional optimization, you can say, well, in general, you can just think about x takes any value in the real line for some function f of x you want to maximize or minimize. And we can find the optimal solution by trying to identify all the local optimal solutions. Unfortunately, this may not be really true. Why?
It's not sure if these are all the points.
I'm sorry?
Maybe the points that you use to find local optimal solution.
Okay.
Maybe there's still, if you don't take all of them,
okay,
maybe the optimal solution, you find at least the optimal solution.
So what Bryce just said is that there might be cases where just by identifying all the local optimal solutions, it's a very challenging task. Is that what you want to comment? Yeah, I tend to agree. And anything else you want to say about this? Well, I guess we still need to recall that the assumption that this is continuous and differentiable objective function, then we can do this. And in some applications, we don't have such a property, then what can we do? Well, we have to, later we are going to say we have to do some kind of line search within certain intervals. Okay, so let's first think about if you have a point x satisfies the derivative f prime of x equals to 0, this is called a stationary point. How to find the stationary point? And why they are important? I think that you can answer. Why they're important? Because these are candidates that we try to examine whether one of these may become eventually your global maximum or minimal, right? And how can we find those points? Well, in general, I need to solve some function f prime of x equals to 0. I need to find all the roots for that. Is that an easy task? I'm sorry?
You can use Newton's method.
I can use Newton's. Can you explain a little bit about Newton's method?
I forgot.
It's an iterative procedure, like to find the root.
To find a root, of course, one easy way you can say is that, for instance, if I want to find a root between the interval a and b, I know f of a is below 0, f of b is greater than 0, so there got to be somewhere in the middle that cross 0, right? And what do?
Binary search.
Well, I just do a binary search, I check the middle point, and then what? I see if that's greater than 0, then I change the interval, cut it into half, and then what? Keep doing. And sometimes you'll say, I know the gradient direction, so I don't want to do binary search. I just interpolate by along this direction, right? And then that's like better than this. And of course, you can iterate. And sometimes you say, I know even second order derivative. I can approximate second order derivative by taking the difference of the slope along the starting point. That's what Sayre just mentioned, like Newton's method. And some people call Newton-Raphson iteration. And these are important numerical techniques later we're going to use also for optimization problem. Okay, so if you're not very familiar with this, I would suggest that you read this optimization textbook. It has mathematical background review on Newton's method and some other important mathematical tools to help you find the root. But with that being said, still, how to really find all possible roots is not a very simple task. For instance, I can give you an example. Maybe let's say sine of 1 over x. Okay? And then that equals to 0. And then how many values can you find for x?
It oscillates as the limit approaches 0, so I think there's no limit.
Well, I'm saying that, for instance, I want sine of 1 over x equals to 0. And then for x, I can have infinite many solutions satisfying that, right? And then what? Can I exhaustively enumerate those solutions? It will be a very challenging task if these are all stationary points. Okay? And usually, if assume that we don't have such a bad problem being optimized, then we can effectively check the second order derivative. If it's positive, then we say it's a local minimum. If it's negative, we say it's a local maximum. If it's equals to 0, then it's either local minimum or local maximum or inflection point, which is something like a not maximal or minimal. But how do we know? Take a higher order derivative, like what Mr. Yu Liu just said. Check the first time you encounter non-zero in the higher order derivative. If that's even order, then you can make a decision based on that. If it's odd, then you just say it's inflection point. Okay? Clear? So for unconstrained optimization, here's what we just said. If you think about the first non-zero or non-vanishing derivative at this stationary point, for even order, you know what to do. If it's odd, then let's see if this is right. If it's even order positive, yeah, I think so. If it's odd, then let me see. If I have even order, then basically I can check, right? It's positive or negative, I can check. It's local minimal or local maximal. If it's odd, then basically it's not. Okay, so here are examples. For instance, the first case, can we find global optimal for unconstrained optimization? First problem, do we have global, is it maximal or minimal? Minimal at where?
0.
Okay, for the second problem, do we have global maximal and or minimal?
No.
No, why not? It's monotonously increasing, right? And without any limit. Okay, and for the third case, do we have local maximal or minimal? For the third case.
It should have cubic behavior.
I'm sorry?
It should have cubic behavior.
So what's your conclusion for the third case?
It's going to do the same thing as X cubed then.
So it will be, you think it will behave similarly to what? To the second problem, where, for instance, when x approaches to positive infinity, this will go unbounded, will go to positive infinity. When it goes to negative infinity, it will go to negative. The f of x also goes to negative infinity. So we don't have, but we don't have global, but we do have local ones. In the second case, we have local ones. Like in this case, we have at 0, right? And in this case, well, you need to do some numerical calculation to find out. And what about this? We have what? We have maximum and minimum. Do we have global maximum? Why not?
They're all global.
They are all global. Okay, so global maximum is 1, right? And global minimum is -1. And of course, even though we have global maximum 1, that's the objective function, the actual values may not be unique. And in this case, you have infinite, countably infinite many possible values of x that can give you sine of x equals to 1 or -1. Okay? Any questions? So for unconstrained optimization, I would say the one-dimensional case is actually not that complicated. All these characterizations are valid only if the objective function is continuous and differentiable. Of course, that's as often as needed. In real life, we may not have such nice property, but still, as an engineer, you may say, I can take numerical approximation of the gradient of the derivative. That's probably good enough for you to practice on this technique. How can we handle functions that are not continuous or not everywhere differentiable? Well, in general, think about it. It's not continuous, so of course it's not everywhere differentiable. But sometimes even it is continuous, it may not be everywhere differentiable, right? So what do we do? Well, we need to identify those points, and that's extra work. We need to examine those points to see whether they are indeed maximal or minimal, right? Okay, so we have to consider explicitly these points of discontinuity or non-differentiability. Okay, so first problem, for this problem, do we have maximal or minimal solution? We have minimal at where? At 0, but how can we identify that? We cannot really take derivative, but but how do we know that's really a global minimum, for instance?
You take in the neighborhood of 0. You can prove that first. It is a local minimum, and then you can prove that no other point is.
Well, in this case, we have to say if you pick any other point, it's greater than x equals to 0. For one-dimensional case, it's easy. And in fact, this is actually a convex function if you look at the definition for convexity. But it's really not differentiable at x equals to 0. What about this? Is this continuous function? No. It's discontinuous. It has discontinuity at where? Okay. Does this function have global maximal or minimal? It has.
Or slightly less than 0.
I'm sorry?
It's a global minimum.
Global minimal.
No. Slightly less than 0.
You talking about the second one?
Slightly less than 0. Yeah.
So. So the function is, and that's important to recognize, even though you think that it should have a global minimum, right? When x approach to 0 from the left, right? But still, because x equals to 0 it equals to 1, so only in the limit this goes to 0, right? Which means what? In fact, there's no real minimal. Well, for this function, because of that, there's no real minimal, right? But we know that it has, if you put a sequence approaching to 0 from the left, eventually you can say the objective function can approach to 0, arbitrarily close, but we don't really have a concrete minimum. Okay, and what about this? What does this function look like?
This is going down, then it shoots back up.
Okay, so what can we say about this function? Does it have local maximal, local minimal?
There's no maximum.
No global maximal, okay. Is there any local maximal?
It kind of looks like it zigs like a sawtooth.
Okay, so how should I draw this? Okay, you want to draw from here? Draw it on this board? Okay. Okay, so.
This is what I think. This right here is your minus.
Can I borrow this for a second?
Yeah, go ahead, take it.
So I will give it back to you. Okay. Thank you. Okay, so. Okay, so I guess this is what we want. This is the function, right?
Yes.
Okay, and then at x equals to 0, which value should I take?
1.
Takes this value. Okay, so I should, okay, and here, this is not discontinuous. This is continuous, but not differentiable. And there's another point another point is, yeah. So, okay, so we do have a local minimum at 2, right? And then,
Would it be global as well?
well, I think it is, right? And, I'm sorry?
That intersect at 2 negative 1.
Should be where? You mean this value? Should go further. Okay, and then what? And then go up. Okay. And that's a local minimum, and also we check that's also global. Okay, very good. Okay, thank you. And so you get some feeling about, in general, for one-dimensional case, what can be done and how complicated this can be if it's not like this toy example. So for this, do we have local optimal solution? Do we have global optimal solution?
Well, the limit approaches 0.
Okay, the limit.
From negative infinity and positive infinity.
Okay.
But it'll never hit 0.
So what do you say?
It doesn't have one.
Okay. Does that make sense? Yeah, okay. So sometimes we can have function that we say there's no local optimal, there's no global optimal. The function is just like that. Okay? And well, when you try to not minimize but maximize, what will happen? The same or different?
It goes up to positive infinity.
Yes. At 0 though, right?
I'm sorry?
It is highest at 0.
When x approach to 0, you actually get the maximum, but the maximum value also approach to infinity. So can we say that? So can we say 0 is the maximum? No. Well, so in this case, still we don't have a solution, right? And what about this kind of problem? F of x, when x is bounded within the interval from a to b, can we always have maximum or minimum? Yes? Why?
Well, if it's between A and B, it's a sure line.
Well, I would say still depends on what happens in the middle, right?
It might go to infinity at one of its endpoints.
Yeah, like the example we showed before, if A and B include 0, then still we don't have maximum, right? For 1 over x squared, right? Yeah, so we could have, but what I'm saying is if the function has bounded value, then we can claim there should be a maximum and minimum when the range of x is also bounded. Yes?
Can you repeat what you said about it? Because I think if it's bounded, there should be a local maximum. But it said,
well, because f of x can also approach to infinity, like this example, right? Yeah. We see that when x approach to 0, this actually can get the maximum value, but x equals to 0, this is actually undefined. So we don't have that. Even if we say, let's assume that x not within the whole real line, we say it's within -1 to 1, still we don't have the maximum, right? Okay, so in this case, we can consider all feasible stationary points plus the boundary, right? So if the function value is bounded, then definitely we can find one. We can find one maximum and one minimum. So if we consider both endpoints, these are all local optima. Local optima we need to consider, and also the stationary points. These constraints are actually simple, right? So we still say that even though you may say this is constrained optimization because we constrain the variable to be within some interval, but still, this is, in fact, we still say it's unconstrained optimization problem. Why? Because these constraints are relatively simple. So we will have to handle more difficult linear or nonlinear constraints later in this course. Okay, so maybe let me try to briefly summarize what we did tonight. I think we talked about optimization problem into two categories. One is called what? Linear, and the other is nonlinear. So we have linear program and nonlinear program. For linear program, we just said it has the objective function has to be linear, constraints have to be linear, right? And later we are going to see that's a special case of convex program. And because of that, we know what? For instance, local optimal solution should be global, right? And also for linear program, we know that the optimal solution will be on extreme point. Well, we also realize that by exhaustively search all the vertices on this polyhedron is not really a computationally affordable algorithm, a technique to solve the problem. So later we have to look into some alternatives, okay? But then we say, well, if we don't have linear program, then what can we do? Well, we need to handle so-called nonlinear program. And the easiest problem we can look at is what? One-dimensional, unconstrained nonlinear program. So we identify, in this case, we need to assume the function is continuous and differentiable. So what? We check first order condition, find the stationary point, and then what? Examine maybe second order derivative, or maybe some other conditions. If you read the textbook, for vector case, we can check the gradient and also check Hessian matrix. And also, if we don't want to check Hessian matrix, at least check the neighborhood if the direction is within the feasible set or not. The inner product between the gradient direction and any feasible direction. We basically need to look into all these conditions to identify those points are local optimal or not, and then try to find the global optimal. Okay? But we also know that if the problem is convex or concave program, meaning that if the feasible set is convex, objective function is also convex function, then we would expect only one local minimal solution, which is also global minimal for convex programming. So we say for nonlinear program, the only thing we know we can find efficient algorithm to get to global optimal solution is convex program. Okay, and of course, next time we are going to talk about, for instance, if it's not convex, what can we do? In general, what we have to do is really what? For instance, try to intuitively think about climb a hill, right? Think about if you have a concave function, you want to find the peak. It's like climb the hill. How do you do that? Very hard, okay. You have to make sure that each step you're actually going what? Up, meaning that you have to increase You have to ascend, you have to increase the value of your objective function. But how do you make sure you can do that? Starting from any feasible solution, how do you make sure you can increase the value of your objective function if you want to get to the peak?
By measuring the distance?
I'm sorry?
By measuring the distance between the 2 points?
Well, in general, you have to find another feasible solution, right? First, how to get to that feasible solution, you can pick any point. But in general, if you randomly pick a point, you cannot say that value, the objective function will have larger value. But some direction you need to look into. Like I think some students already know. It's like you what? For instance, you find some direction called gradient, which means what? In one-dimensional case, it's like what? Starting from a point, like a Newton's step, right? You take the tangent line, your approach to the tangent line.
The easiest way up.
The easiest way up is like, for instance,
you don't want to take, if you,
but remember, this tangent line is only what good for a small neighborhood at that point. So we got to say, well, if you follow this direction, it will be good if you go for a small step. If you go for a large step, you never know what will happen. But fortunately, you can say we know how to do what? One-dimensional optimization. So what? We say, well, I don't know what step size would be good, but I can do so-called line search to say, well, along this, from 0 to some arbitrary positive value, which step size would be good, would give me the maximum increase of the objective function. Make sense? And that's one important mathematical technique. Later we are going to talk about so-called gradient descent or gradient ascent to find the minimum or maximum. Okay, so I guess I have new homework assignment posted on Blackboard, and some very keen students already started the second computer assignment, which I think require a lot of after-class reading, but I do encourage you to read the textbook and before the class and also the lecture notes. And also I would suggest that from next time, we are going to have maybe some volunteering students take turns doing the recitation notes, which I usually feel very useful for other students to actually review the course material and also discuss about questions beyond just the presentation slides that I gave. Okay, so bear that in mind. I think the later lectures will require maybe some mathematical background and also certain terminology that we used before we will repeat for some time. So please also review some background material in the textbook as well as the presentation slides. If you do have questions, feel free to stop by. And another way to interact, I think, is through so-called course Blackboard discussion forum. You can post your questions or even start a thread of the discussion, and also encourage all students try to be active in checking the update on course Blackboard. And if you have not submitted your first homework assignment, please try to submit by tonight. If not, you can always send me the electronic version of your homework or computer assignment through my email, or maybe you can use a course Blackboard digital Dropbox and just send me an email reminder if you have a large file to submit. And for computer assignment, I would suggest that you submit electronic version so that it's easier for me to run your MATLAB program and see the results in the future. Thank you. And that's it for tonight.
Could we borrow you for a few minutes?
Sure, yeah, I will. Okay, thanks. Suggest to read. Well, I think the first part 2, unconstrained optimization in the textbook.